Hey there, welcome to a video discussing pages 8 and 9 of the section 3.2 notes. So we're going to wrap up section 3.2, and here we're starting off with the alternative definition for a derivative at a point. So you might remember we did talk about this in the homework not that long ago. So if I actually do click on homework images, and I think it was homework number 10 if I'm not mistaken. There we go. So section 3.1, and there was this weird limit definition of derivative, a little different than what we've done before up here. So we see this f prime of a equals limit as x approaches a, f of x minus f of a over x minus a. We're going to explore that right now. So it's the same thing as what we were doing before with the whole a plus h and a, but just another way of expressing it, and it's kind of good to recognize it because on the AP they do expect you to recognize that this is a derivative. So here's a comma f of a, here's a plus h comma f of a plus h, and we know this, right? We know that the slope of the secant line is going to be f of a plus h minus f of a over a plus h minus a. And of course, a's cancel, and you just get h on the bottom. And then the slope of the tangent line will be the limit as h approaches 0 of that same junk that you see right above. Because as h approaches 0, Q gets closer to P. Now we're going to do the same thing, but now we have different variables for point Q. So you're going to do f of x minus f of a over x minus a. But you want Q to get closer to P, or you want x to get closer to A. Whereas here we want h to get closer to 0, so that this becomes, Q becomes P. So you're going to take the limit as x approaches a of that junk you see right above. And that right there is going to be another way we can find the derivative. And again, we want Q to get closer to P so that we can go from a secant line to a tangent line. So let's use this definition for evaluating the derivative in example 8 down below. So over here, where you ask to use the alternative definition to find f prime 11 for f of x equals root x minus 2. So let's do it. F prime of a, again, equals the limit as x approaches a of f of x minus f of a over x minus a. Or f prime 11 will equal the limit as x approaches 11. And by the way, you're going to use this to find a numerical value of the derivative, not a derivative expression, just so you know. Should mention it earlier. So you have f of x, which now I know is a root, well, I'll just leave it as f of x for now, minus f11 over x minus 11. Then I'm going to substitute for f of x and put in root x minus 2. So root x minus 2. F11 is root 9, which is 3. Remember, that's going to be root 11 minus 2, which is root 9, which of course you know is 3, over x minus 11. At this point, you should know what to do. We're going to do the whole conjugate thing that we've done before. So you're going to do root x minus 2, but plus 3 to go top and bottom. And I'm not going to FOIL the bottom because I'm hoping for things to cancel. So I'm going to kind of leave the bottom as is, but I'm going to FOIL up top. If I FOIL up top, the limit as x approaches 11. If I FOIL up top, I have x minus 2 minus 3 root x minus 2 plus 3 root x minus 2 minus 9. Down below, x minus 11, root x minus 2 plus 3. Those cancel. So I get x minus 11 up top. I get x minus 11 down below. Those cancel. And I have root, oh geez, that's ugly looking. Let's undo that. root x minus 2 plus 3. Those cancel. Again, you're taking limit as x approaches 11. So now you got 1 over root x minus 2 plus 3, and I got to tuck in that limit notation. Can't get lazy about it. Now I can plug in 11. Now I'm golden. If I do that, I get 1 over root 11 minus 2 plus 3. That's 1 over 3 plus 3. Can't do these 3's in this Zoom thing. So I get 1/6 as my answer. So that's how that goes. And we'll do some practice on the worksheets. We'll do some worksheets, I think, for homework after Wednesday's class. So that's alternative definition of the derivative. Now, intermittent value theorem for derivatives. If a and b are 2 points in an interval in which f is differentiable, then f prime takes on every value between f prime of a and f prime of b. So this reminds us of the IVT for continuous functions, which we talked about at the end of 2.3. We did talk about that. And remember, a function that is a derivative will exhibit IVT behavior even if the derivative itself is not continuous, just so you know. Like for example, we have seen, like if you have absolute value, for example, right? So that's of course continuous. Actually, that's probably not the best example. Sorry. Let me come back to this part right here because I'm not 100% sure of a good example to share with you guys. But if your derivative itself, like let's say, I don't know, like let's say this is the derivative here. Let's say that represents a derivative. If function has a derivative, we'll exhibit IVT behavior even if it's not continuous. But I think I'll need to revisit that probably when I see you guys on Wednesday because I'm still not quite sure what that means. But what's happening here, just at its core for IVT, is that as long as your function is differentiable, which means you are continuous, you're also going to be continuous when you're differentiable, the function, the original function. And let's say, I don't know, I guess I'm like this here, which of course looks differentiable to me from a to b, then whatever the derivative is at f at a and derivative at b, any derivative in between can be taken on. So for example, say f prime of a were like 1, f prime of b were 4, then there can be an f prime value c that's between 1 and 4, where c would be right in the middle of a and b. That's what that's telling us, the IVT for derivatives. So let's look at an example here. Suppose you're given a mystery function f, you don't know what it is, but you do know it's differentiable on an interval from -2 to 5. And you know the derivatives from -2 to 5. Again, let's kind of draw this. So -2 is right here. You got a function and it has a negative derivative, so it's probably going to be looking kind of like this. And then you get the 5 and it has a derivative that's positive. So it's probably positive slope here, negative slope there. So what this tells us is that if you choose an x value that's in between -2 and 5, any derivative between -0.8 and 2 has to be taken on. So for example, can my derivative equal 1? Sure. That's because this number, -1, is between -0.8 and 2. So absolutely you can. Can it equal -0.3? Sure. Because -0.3 is in between -0.8 and 2. So, for example, can the slope equal 1? Probably, like over here. Well, probably, it will. Or like -0.3. Sure, probably maybe somewhere over here where it was slightly negative. Can it equal 0? Sure. Again, probably somewhere over here it could be 0. And 0 is between -0.8 and 2. And so how do we know again? IVT for derivatives tells us that. What important key piece of information did you need to know about F to be able to make your conclusions? Well, F had to be differentiable, not just continuous, because continuity doesn't guarantee differentiability, but of course you do need continuity. It has to be differentiable on -2 to 5. Now, let's scroll down. Will there be some x value in this interval where f prime c equals 4? Maybe, but we don't know. But no guarantee. It can, but there's no guarantee. That's because 4 doesn't fall between -0.8 and 2. Let's wrap this up with example 10. So given a function g that's continuous on 3 to 7, and you have g prime 3 is -4, g prime 7 is 1.5, will g have a horizontal tangent? And the answer is yes. Horizontal tangents have a slope of 0. That means that the derivative, g prime of c, or because we'll use x instead, g prime of x will have to equal 0, and 0 is clearly between these two numbers here. But I made a mistake. I wish actually I said that I made this mistake on purpose, but I just realized my error. What error did I make? Continuous is not necessarily differentiable. Just because you're continuous. Now, if you had g of 3 and g of 7 without the derivatives, then sure. Then you could say, there's some g of x value that equals 0. But because we're talking about derivatives, you need to say differentiability. So actually, I kind of screwed up there. The answer is actually will g have? We're not sure. So did catch myself there. And if you think about it, you could have, yeah, sure, you're continuous, but what if you have like some weird corners or stuff like that? Like, so g prime of 3, so x equals 3. Let's say it's a pretty steep slope. Let's say I have a sharp corner here. And then g of 7. So you had like kind of like a weird piecewise function like that. These are both linear. So that's -4 and that's 1.5. It's not differentiable in between the two because of that sharp corner. So therefore I can't say that I'd have a horizontal tangent there. So the major takeaway is that this theorem would be unnecessary if all derivative functions were continuous. And we know that so in this case, all derivative functions, not all functions, but not all derivative functions are continuous. So obviously this right here is my original function, and if I did my derivative function, it would not be continuous. It would look like this here down below. If I put like x equals c. So again, this theorem would be unnecessary if all derivative functions were continuous because IVT for continuous functions would be sufficient. So we have to make that statement about differentiability. Therefore, if all you know about f prime is say some values in the table, don't assume f prime is necessarily continuous. And when f prime will not be continuous if you're not fully differentiable in the original function. So these are things we'll discuss again and come back to when we meet as a class. And that's the end of the video.